So, imagine for a second that you accidentally drop your smartphone into a blazing wood-fired pizza oven.
Oh, wow. Yeah, that is a terrible start to the day.
Right, absolute nightmare. And we are talking about an environment sitting right around 700 degrees Celsius, which is roughly 1300 degrees Fahrenheit.
Yeah, that's incredibly hot.
Exactly. And your first thought is probably about the glass shattering or, maybe the plastic battery casing melting into this terrifying puddle. But long before any of that macroscopic physical destruction happens, the actual brain of your phone,
The memory chips.
yeah, the memory chips, they would suffer permanent, completely irreversible amnesia. Like all the data, the photos, the operating system just, gone.
It's just a completely hostile environment for modern electronics. And while you, listening right now, hopefully won't ever need your personal devices to survive a trip through a pizza oven.
Let's hope not.
Yeah, humanity actually desperately needs smart electronics that can survive those exact conditions. I mean, we are pushing into these frontiers where traditional hardware just it completely fails.
Well, welcome to the Deep Dive Lab. Today we're exploring a microscopic mystery that was published in the journal Science back in March 2026.
It's a fascinating paper.
It really is. The research comes from this massive collaboration between Dr. Jian Zhao and Dr. J. Joshua Yang from the University of Southern California, along with teams from the Air Force Research Lab, Kumamoto University, and a tech company called Tetramem.
Right.
And the core question we are unpacking today is basically, why exactly does computer memory fail when things get too hot? And, more importantly, how did this specific team engineer a tiny memory device that can survive temperatures that are literally hotter than a jet engine's exhaust?
Yeah, and this is one of those papers that just completely shifts our understanding of physical limits.
Yeah,
I mean, for decades, the heat barrier was just this accepted reality in electrical engineering.
like a hard limit.
Exactly.
Yeah.
We always assumed you just had to build these elaborate, bulky cooling systems if you wanted computers to operate anywhere near extreme heat.
Okay, so before we get into the actual breakthrough, let's establish the baseline problem here. If I'm looking at the flash memory inside my laptop or my phone, why can't it handle the heat? Like, what is physically happening to the hardware when the temperature spikes?
Well, conventional silicon devices, they start experiencing massive reliability issues once the temperature climbs over roughly 200 degrees Celsius.
All right.
The materials just start degrading. Now, scientists have, of course, tried alternatives for these extreme environments.
Yeah.
One approach is phase change memory,
All right.
and this encodes data by physically changing a material from an amorphous state to a crystalline state.
Oh, okay. Wait, let's pause there because amorphous and crystalline can sound a bit, dense. Are we basically just talking about how organized the atoms are?
Yeah, that's a really good way to look at it. Think of the amorphous state like a jumbled random pile of bricks just dumped on the ground.
Okay.
And the crystalline state is when those exact same bricks are perfectly organized and stacked into a neat wall.
Got it.
So by forcing the material back and forth between, jumbled pile and neat wall, you can encode your ones and zeros.
Okay, so what does the heat do to that system?
Heat is basically just ambient energy, right? So around 200 degrees Celsius, there's so much thermal energy bouncing around that the jumbled pile of bricks will actually spontaneously organize itself into a neat wall.
Oh, weird.
Yeah. The material recrystallizes on its own without us ever telling it to. And when that happens, any data you had stored in that jumbled state is just instantly wiped out.
It just overwrites itself. That is incredibly frustrating.
Very.
So what else have they tried?
Well, they've also looked at ferroelectric memories. These use electric polarization to store data. So picture millions of tiny compass needles inside the material.
Okay, compass needles.
If we force the needles to point up, that's a 1. We force them to point down, that's a 0. But again, heat is just microscopic shaking. So when the temperature gets extreme, the thermal agitation shakes those compass needles so violently that they just completely lose their alignment. The data scrambles.
Okay, so if conventional silicon and the phase change memory and the ferroelectric memory all basically tap out around 200 degrees, how was this research team planning to hit 700 degrees?
Right, so they focused on a completely different technology altogether, something called resistive switching memory, or memristors.
Memristors. Okay, so for you listening, let's visualize how a memristor actually works. Imagine you are trying to build a tiny microscopic bridge across a river.
Hmm.
To turn the memory on to encode a 1, you apply an electrical voltage. And that voltage pushes these tiny structural gaps, which are called oxygen vacancies,
All right.
across the material.
Yeah.
It basically lines up stepping stones to build a conductive filament, like a bridge. Then, to turn the memory O off F and encode a 0, you reverse the voltage, you pull the stepping stones away, and you break the bridge.
And what's really fascinating there is that those oxygen vacancies aren't even physical objects.
Wait, really?
Yeah, they're literally the absence of oxygen atoms in a crystal grid. Think of, those sliding tile puzzles where there's always one empty square.
Oh, yeah, the plastic ones where you shift the picture around.
Exactly. Applying voltage just moves that empty square around to form the conductive path. And in the lab, the standard way scientists built these memristors was by creating this tiny 3-layer sandwich.
Okay, and what exactly is in this sandwich?
So the bottom layer is an electrode made of platinum. The middle layer, the river in your bridge analogy.
Right.
So it's switching material called hafnium oxide. And then the top layer is another electrode made of tungsten.
Platinum, hafnium oxide, tungsten. I mean, it sounds incredibly durable. Those are heavy-duty metals.
Oh, room temperature works beautifully.
Right.
But when researchers tested this specific device at high temperatures, they ran into a very strange mystery.
What happened?
The device would just permanently break. It would get permanently stuck in the on-end state. The bridge would form, but no matter how much reverse voltage they applied, they just couldn't break the bridge back down.
Wait, so does the heat just melt the tungsten and the platinum together?
Not exactly melting, but you are definitely on the right track.
Yep.
The high temperatures give the atoms in the top tungsten layer way too much thermal energy. They get incredibly jittery.
Okay.
And the heat essentially acts as a catalyst, allowing those tungsten atoms to break loose, migrate down across that middle hafnium oxide layer, and basically pile up on the platinum bottom layer.
Oh, wow.
Yeah, they create this permanent short circuit.
So it's less like building a neat little bridge of stepping stones and more like a windstorm just blowing all the materials into a permanent fused clump.
A very stubborn clump, yeah.
Yeah.
And this is exactly where the team from USC and their collaborators came in. They decided to change just one single ingredient in that device sandwich.
Okay.
They took out the bottom layer of platinum entirely and replaced it with a single two-dimensional layer of graphene.
Just to be clear, graphene is carbon, right? It's literally a sheet of carbon atoms that is just one atom thick.
Yes, exactly. So the new structure was graphene on the bottom, hafnium oxide in the middle, and tungsten on top.
See, that seems like a massive downgrade in armor to me. You're taking out this dense slab of platinum and putting in a microscopic sheet of carbon to defend against, like, extreme heat.
I know, it sounds counterintuitive.
But the data they published in the science paper showed this swap completely solved the problem.
The results were genuinely staggering. They maintained this massive, reliable difference between the on-N and off-F states, all the way up to 700 degrees Celsius.
That's wild.
And they ran the device for over 50 continuous hours at that temperature without needing to refresh it even once.
I remember reading this part of the paper, and I just found it hilarious. The 700-degree mark wasn't actually the limit of the new memory chip, was it?
No, it wasn't. The memory chip was doing just fine. 700 degrees was actually the absolute maximum limit of the heating equipment in their laboratory.
Oh, my God.
Yeah, the probe station literally couldn't get any hotter without damaging itself. So this tiny microscopic chip outlasted the heavy-duty testing rig.
That is just incredible.
They also proved it could endure over 1 billion switching cycles. They turned it on and off 1 billion times in what was essentially a simulated inferno.
1 billion times.
Yeah, and for context, that kind of endurance is about 6 orders of magnitude better than any other non-volatile memory tested at those extreme temperatures.
Okay, so the swap worked. The one atom-thick layer of carbon saved the day. But we really need to explain why, because right now, to a lot of people, it probably sounds a bit like magic.
Right.
How exactly does a single sheet of carbon stop a flood of superheated tungsten?
So, to figure that out, the team had to look at these devices at the atomic level. They used some incredibly advanced imaging techniques, specifically high-resolution transmission electron microscopy, or HRTEM, and electron energy loss spectroscopy.
Okay, wait. I know what an electron microscope is, but what is electron energy loss spectroscopy?
Well, right. It's basically a way of identifying materials. You shoot a beam of electrons through a sample, and when those electrons hit different atoms, they lose a very specific amount of energy.
Oh, I see.
So by measuring exactly how much energy is lost, You can map out exactly which chemical elements are sitting where, literally atom by atom.
So they basically baked these devices at massive temperatures, sliced them open, and mapped the microscopic crime scene.
Yes. And the crime scene was very revealing. In the old platinum devices, the ones that failed, they found what the authors described as a mushroom-like protrusion.
A microscopic metal mushroom growing inside the chip.
Yeah, exactly. The tungsten had bled completely through the middle layer and grown this massive, ugly mushroom structure right down into the platinum. It was an uncontrolled, permanent bridge.
Okay.
But then they looked at the new graphene devices, and the interface between the middle layer and the graphene was just razor sharp. The tungsten had stayed exactly where it was supposed to be. It hadn't bled through at all.
I'm still sort of stuck on the physical mechanics of this, though. Why does platinum let the tungsten grow into a giant mushroom, but graphene just stops it cold?
Well, this comes down to something called density functional theory. The researchers ran these massive, complex quantum mechanical computer simulations to measure the absorption energy between the materials.
Adsorption energy.
Yeah, absorption energy is basically a measurement of how strongly one atom wants to stick to a surface.
Okay, so like atomic stickiness.
Atomic stickiness, exactly. The computer models showed that tungsten absolutely loves platinum. It has a very high negative absorption energy with platinum, specifically negative 9.08 electron volts.
Wow. Okay, so platinum is basically acting like a super absorbent sponge for tungsten.
That is a perfect analogy.
Mm-hmm.
The platinum actively pulls the tungsten in. It serves as a sink. When the device gets hot, the tungsten atoms break loose, and the platinum essentially sucks them down to the bottom.
Right.
And once they hit that platinum surface, they spread out incredibly fast because there's very little friction or diffusion barrier on the platinum. They clump together, they build that mushroom protrusion, and they short out the device.
But then we swap in the graphene.
Right. When they ran the exact same simulations for graphene, the absorption energy for tungsten was near zero.
Okay, so if platinum is the super absorbent sponge, graphene is like a high-end, non-stick Teflon pan. The tungsten just slides right off.
Yes, that's functionally exactly what happens. But to explain why it acts like a Teflon pan, we have to look at graphene's physical shape. Graphene is chemically inert. Its carbon atoms are arranged in a perfectly flat, tight, hexagonal lattice. It looks a lot like chicken wire.
Okay, chicken wire. Got it.
In that chicken wire shape, every single carbon atom is perfectly bonded to its neighbors. There are no loose chemical bonds reaching out into space looking to grab onto something else. It's entirely self-contained.
Ah, so it has no free hands to grab the tungsten.
Exactly. The atomic interaction is so incredibly weak that it is energetically unfavorable for the tungsten atoms to attach to the graphene surface, or to cluster together, or to grow into a permanent bridge.
That makes so much sense.
Yeah, graphene acts as this impermeable, non-stick shield. Even when the device is baking at 700 degrees and those tungsten atoms are super jittery, they just have nowhere to go and nothing to grab onto. The electrical separation is completely preserved.
Man, this is just a brilliant piece of detective work, but I do want to zoom out here for a second because we've been talking about a single microscopic short circuit. How does fixing this one tiny bridge translate into a technological leap for the listener? Like, are we ever going to see this outside of a university lab?
Oh, definitely. This is where the story gets much bigger than just a single test chip. The research team didn't just build one memristor. They successfully built a 32 by 32 crossbar array of these devices.
Oh, wow.
Yeah, that is over 1,000 memristors all wired together on a single chip.
And did they actually work? Because usually when you try to scale up experimental nanoelectronics like this, everything just breaks.
They achieved an 81% functional yield right out of the gate.
81%.
Yes. Getting 81% of a 1,000-device experimental array to work on the first try is highly unusual in this field. It really proves this isn't just some bespoke science fair project. It's scalable, and it's actually ready for large-scale foundry manufacturing. But honestly, more importantly, it's about how these devices compute. They aren't just storing simple ones and S's.
Wait, what do you mean? I thought memory was all binary, just on or off?
For traditional memory is binary, sure, like a light switch, but these memristors act a lot more like a dimmer switch.
Oh, okay.
The researchers were able to program these individual devices into 32 distinct resistance states at 700 degrees Celsius.
So instead of just black and white, we have 30 shades of gray in between.
Yes, and that is a profound shift because it allows for something called in-memory computing or analog computing. It actually mimics the way the synapses in our human brains work.
Okay, walk me through that. How exactly does a 32-state dimmer switch mimic a human brain?
Well, in your brain, a synapse doesn't just turn on or off. The connection between neurons can be weak, it can be strong, or it can be anywhere in between.
Right.
And that varying strength is what allows us to learn, to weigh different variables, and to recognize complex patterns. By having 32 different resistance states, this new hardware can physically process weights and variables exactly like an artificial neural network does.
Okay, I see where this is going. Because normally, a regular computer has to fetch data from the memory, drag it all the way over to the processor, do the math, and then drag it all the way back to the memory. And that shuffling takes a lot of time and energy.
Yes, it's called the von Neumann bottleneck. And it's basically the biggest limitation in modern computing today. But with in-memory computing, the chip just does the math inside the memory itself.
That's amazing.
It allows for incredibly complex, energy-efficient artificial intelligence operations without constantly shuffling data back and forth.
So we aren't just talking about a hard drive surviving a fire. We are talking about putting a continuous, functioning AI brain inside the most hostile environments imaginable.
Exactly. I mean, think about autonomous vehicles. Right now, the sensors have to be heavily protected or kept far away from the hottest parts of the engine. With this technology, you could mount smart sensors directly inside the combusting engine to process performance data in real time.
Or think about geothermal energy. We want to drill miles into the Earth's crust to tap into limitless clean heat.
Yes.
But right now, the drill bits go blind because the sensors literally melt. If we can put AI-capable chips right on the drill heads, they could navigate those complex rock formations autonomously at massive depths.
And, of course, space exploration. We've always struggled with Venus. The surface temperature there is a constant 475 degrees Celsius, and, it rains sulfuric acid.
Not a great vacation spot.
No, definitely not. The Soviet Venera probes back in the 70s and 80s only lasted a couple of hours before their electronics completely cooked.
But with a graphene-based memristor, you could theoretically have a long-term rover with advanced brain-like AI exploring the Venusian surface. It could process data, navigate obstacles, and make decisions continuously without the heat ever wiping its memory. It really feels like we just unlocked a cheat code for exploring the solar system.
It really does open doors that have been welded shut for decades.
Well, let's summarize the 3 key takeaways from this incredible paper for you to remember as we wrap up. Number 1, extreme heat usually destroys computer memory because it scrambles the atoms, causing them to migrate and create permanent short circuits. Number 2, replacing a standard metal electrode with a 2-dimensional layer of graphene acts like an impenetrable non-stick barrier that completely stops that destructive migration. And number 3, this really elegant swap unlocked AI-capable analog memory devices that can survive past 700 degrees Celsius for over 1 billion cycles.
And, there's a much broader insight here about how science actually progresses. To push our capabilities into entirely new frontiers, you don't always need to reinvent the whole machine from scratch.
Right.
You don't always need some exotic, magical new material. Sometimes you just need to master the interface. By understanding the microscopic boundary where 2 materials meet, by figuring out why tungsten loves platinum but completely ignores graphene, these researchers solved a massive macro-level engineering problem.
It really is a testament to looking closer rather than just looking bigger. Which leaves me with a final thought for you to mull over as you go about your day. If a simple layer of carbon, literally just one single atom thick, can act as an impenetrable shield to protect our most advanced electronics against absolute infernos, what other extreme, seemingly impossible environments in the universe might suddenly be within our reach?
Great question.
Thank you so much for joining us today in the Deep Dive Lab. If you enjoyed uncovering the scientific mystery with us, be sure to follow and subscribe so you don't miss our next deep dive into the fascinating stories hiding right at the edge of human knowledge.